There's a planet in our solar system where the wind never stops screaming. Not a metaphor, not poetic exaggeration, an actual, measured, continuous wind, faster than anything ever recorded on any other world, blowing without pause, without mercy, every single second, for as long as anyone has been watching. We named it after the calm, deep god of the sea. It is not calm. It is not gentle. It might be the single most violent place in the entire solar system, and almost nobody has ever heard of it. Hello, and welcome to Somniora Mind. I'm glad you're here. If a story like this one is the kind of thing that helps your mind unwind before sleep, consider subscribing or leaving a comment to let me know you were here tonight. There's no poster of this planet on any child's bedroom wall, no blockbuster film named after it, no mythology built around it in the modern imagination. Most people, even the ones who sat through an entire semester of astronomy class, couldn't point to it on a diagram of the solar system if you asked them to. And yet, right now, tonight, it's still out there, spinning in near total silence, 4.5 billion kilometers from the sun, so far away that sunlight itself needs 4 hours just to reach it. So far away that exactly one human spacecraft has ever laid eyes on it up close, one single time, decades ago, and never again. We call it Neptune, and it may be the most violent planet in the solar system. The fastest winds ever measured on any world happen there. Storms the size of entire planets appear from nothing and vanish without explanation happen there. A literal rain of diamonds, falling continuously from the clouds toward the planet's core, happens there. A moon locked in a slow-motion collision course, orbiting backward, doomed to be torn apart, circles there right now. And almost none of us have ever bothered to look. Let's start by understanding just how far away Neptune actually is, because the scale of it is genuinely difficult to hold in your mind. Imagine shrinking the sun down to the size of a football. At that scale, Earth becomes a single peppercorn, sitting about 30 meters away. Jupiter becomes a grape, 150 meters out. Saturn, another grape, 280 meters away. And Neptune becomes another lonely peppercorn, sitting 900 meters from that football-sized sun, 9 full city blocks of distance separating it from the star it orbits. That's the real scale of our solar system, and it's exactly why Neptune tends to slip out of memory so easily. It sits so far out there that we didn't even find it by looking up. We found it by doing math. In 1846, 2 astronomers working independently, one French, one English, both noticed something strange happening to Uranus. Its orbit wasn't behaving the way Newton's law said it should. Something out there was tugging on it, pulling it slightly off its expected path, again and again, in a pattern too consistent to be random error. Both astronomers calculated, using nothing but pure gravitational mathematics, exactly where an unseen planet would need to sit in order to cause that exact wobble. Someone pointed a telescope at those precise coordinates, and there it was. A blue planet, waiting patiently in the dark, exactly where the numbers said it had to be. Neptune wasn't discovered by observation. It was discovered by prediction, confirmed only afterward by a telescope pointed at a spot in the sky that mathematics had already claimed with confidence. Neptune sits so far from the Sun that a single Neptunian year, one full orbit, takes 165 Earth years to complete. Neptune sits so far from the Sun that a single Neptunian year, one full orbit, takes 165 Earth years to complete. And yet, despite that impossibly slow year, Neptune's day is shorter than our own. The planet completes a full rotation in only about 16 hours, spinning considerably faster on its axis than Earth does. even while it crawls almost imperceptibly slowly around the sun. It's a strange contradiction to picture, a planet where the days pass by almost in a rush, while a single year stretches out far beyond any human lifetime. An entire Neptunian year longer than the oldest confirmed human beings have ever lived. Since its discovery in 1846, Neptune has completed exactly one full trip around the Sun. 1. Our entire recorded relationship with this planet, every year of it, fits inside a single Neptunian orbit. The American Civil War happened inside that 1 year. Both world wars happened inside that 1 year. The moon landing, the invention of the internet, the rise of the smartphone in your pocket right now, all of it happened inside that same single, slow, patient lap around the sun. We named this planet after the god of the sea, as though its blue color meant something peaceful, something deep and mysteriously calm in the pleasant sense of the word. It isn't peaceful. It's the one place in our solar system where the laws of physics seem to take things personally. By every reasonable expectation, Neptune should be dead. Sitting 4.5 billion kilometers from the sun, it receives only about 1/900th of the sunlight Earth gets, an amount of solar energy so faint that when Voyager 2 approached the planet in 1989, scientists genuinely expected to find a smooth, featureless blue ball. No dynamic atmosphere, no storms, no motion worth mentioning. A frozen corpse of a planet, still and silent, because without solar energy, there shouldn't be enough fuel to drive any real weather at all. What they found instead were the fastest winds ever measured on any planet in the solar system. Sustained winds averaging around 1,600 kilometers per hour, with gusts exceeding 2,100. To put that in perspective, consider Hurricane Patricia, the strongest hurricane ever recorded striking Earth, back in 2015. Patricia's peak winds reached roughly 345 kilometers per hour, and that was enough to tear palm trees out of the ground, flatten buildings, and end human lives. Neptune blows nearly 6 times harder than that, not in a single burst, not as a rare, catastrophic peak. Constantly, without pause, without rest, somewhere in Neptune's atmosphere, at every single moment, winds are moving at the speed of sound. So where does all that energy come from? That's a question nobody has fully answered, even now. The leading suspicion is that Neptune generates its own internal heat, something happening deep within the planet that releases more than double the energy the planet actually receives from the sun. Some of it may be leftover heat from Neptune's formation 4.5 billion years ago, heat that simply hasn't had the chance to fully escape yet, even after all this time. Another proposed mechanism involves helium rain, tiny droplets of helium condensing deep within Neptune's interior and slowly sinking through the surrounding hydrogen, converting gravitational energy into heat as they fall, essentially squeezing warmth out of the planet's own ongoing internal settling. A third possibility involves the planet's interior still gradually contracting under its own weight, ever so slightly, a slow gravitational compression that releases energy as heat, the same basic principle that once powered the sun's own energy output for a brief period, long before nuclear fusion ever ignited inside it. None of these explanations has been fully confirmed, and it's entirely possible more than one process is contributing simultaneously, layered together somewhere in the planet's crushed, largely unreachable interior. Whatever the precise combination, that internal heat rises up from deep within the planet and drives its atmosphere into an ongoing, permanent state of fury. Neptune doesn't need the sun to be violent. It's violent from the inside out, powered by something buried in its own heart that we still can't fully explain. Let's sit with that for a moment. because it genuinely reframes everything else we're about to explore tonight. Most of the weather we understand, hurricanes, tornadoes, blizzards, ultimately traces back to the sun. Solar heating drives temperature differences drive pressure differences, and pressure differences drive wind. Take away the sun's energy, and Earth's weather would eventually grind to a halt, all its violent, churning storms slowly settling into stillness. Neptune doesn't play by that rule. It has built its own internal engine, one that keeps its atmosphere in a permanent state of supersonic chaos regardless of how little warmth the distant sun manages to send its way. It is, in a very real sense, generating its own storm, out of its own leftover birth heat, for billions of years, with no end in sight. Try to actually picture standing there, if such a thing were even remotely survivable. There's no ground to stand on in any ordinary sense, no solid surface separating atmosphere from interior, just a gradual, endless deepening from thin, freezing gas into thicker, warmer, more crushing fluid the further down you traveled. Overhead, faint sunlight, 1,000 times fainter than what reaches Earth, would cast the palest, most distant version of daylight imaginable, more like a deep, perpetual twilight than anything resembling an ordinary afternoon. And through that dim, blue-tinted gloom, wind would tear past at speeds no structure built by human hands could possibly withstand, an unbroken, howling roar, indifferent to the fact that nothing has ever been there to hear it. As Voyager 2 closed in on Neptune in 1989, its cameras captured something that genuinely shouldn't have been there at all. A dark patch, roughly the exact size of planet Earth, spinning steadily in the planet's southern hemisphere. A storm, but not the kind of storm astronomers were used to seeing on giant planets. Jupiter's Great Red Spot had already been swirling for centuries, possibly millennia, anchored, predictable, essentially a permanent fixture of the planet's atmosphere. This storm on Neptune behaved nothing like that. It appeared, then disappeared. It changed shape. It drifted without any obvious pattern. Astronomers called it the Great Dark Spot. 5 years later, in 1994, the Hubble Space Telescope turned its attention toward Neptune, hoping to photograph the same storm in sharper detail. The Great Dark Spot was gone, not shrunk, not drifted somewhere out of view, simply gone, as though it had never existed at all. And then, not long after, an entirely new dark spot appeared, in a different latitude, with a different shape. Hubble photographed that one too. Eventually, it also vanished. This pattern hasn't stopped. Every so often, a fresh dark spot emerges somewhere on Neptune, grows to monstrous proportions, persists for a few years, and then simply fades away, as though the planet had grown bored of it and quietly switched it off. Try to picture that properly. A storm the size of an entire planet, forming out of seemingly nothing, lasting for years, churning at supersonic speeds, devastating everything in its path across an entire hemisphere. And then, without any dramatic conclusion, without any obvious trigger, simply ceasing to exist, as though Neptune itself had decided the performance was over. On Earth, storms follow rules. They form where warmth and moisture gather. They travel along predictable currents. They weaken and die the moment they make landfall, losing their fuel source the instant they lose contact with warm ocean water. Neptune doesn't appear to follow any of those rules. There's no landfall to kill a storm there, no coastline to rob it of energy. There's only a planet, seemingly inventing and erasing its own hurricanes on a whim, storms the size of worlds treated almost like passing thoughts. Scientists still don't have a complete explanation for exactly why these dark spots form, or exactly why they vanish so abruptly. The leading theories involve interactions between different layers of Neptune's atmosphere, methane ice clouds forming at the storm's edges, and deep currents rising and falling within the planet's interior, dragging these vast, dark vortices along with them until some subtle shift in temperature or pressure we haven't fully mapped yet, finally pulls them apart. What we do know is that these storms are genuinely enormous, genuinely violent, and genuinely unpredictable, appearing in different locations at different times, with no fixed schedule and no obvious warning. Neptune keeps building hurricanes the size of entire worlds, and keeps quietly, methodically taking them apart again, over and over, in a cycle no human being has ever managed to fully explain. The contrast with Jupiter becomes almost unsettling once you sit with it directly. Jupiter's Great Red Spot has been under continuous observation for well over a century and a half, and evidence suggests it may have existed for centuries before anyone even pointed a telescope its way. A single, colossal storm that has simply refused to die, anchored firmly in place by the surrounding structure of Jupiter's banded winds. Neptune's dark spots do the opposite. They're born, they rage, and they die within a handful of years, sometimes less, vanishing as completely as if they had never formed at all. Voyager 2 even caught a much smaller, much faster storm racing alongside the original Great Dark Spot during its 1989 flyby. A bright, compact feature that circled the planet so much more quickly than its surroundings that the science team nicknamed it, almost affectionately, Scooter. 2 planets, both giant, both banded with roaring winds, and yet one builds storms meant to last for centuries, while the other seems to build them, almost carelessly, only to tear them apart again within a single human lifetime. Beneath those storms, beneath the blue methane clouds that give Neptune its striking, deceptive color, something happens that sounded, for decades, like pure science fiction. It rains diamonds. Not a metaphor, not poetic language stretched for effect. Genuine, confirmed physics, recreated in a laboratory in 2017 and independently reconfirmed again in 2022. At Stanford University, researchers recreated the crushing conditions found deep inside Neptune's interior using extraordinarily powerful X-ray lasers and watched, with their own instruments, exactly what happens under those conditions. Here's how it works. Neptune's atmosphere is made primarily of hydrogen, helium, and methane. That methane is what gives Neptune its deep, striking blue color, but methane is also, at the molecular level, simply carbon bonded to hydrogen. Descend thousands of kilometers into Neptune's interior, and the pressure becomes genuinely crushing, millions of times greater than the atmospheric pressure at Earth's surface. Under that kind of pressure, methane molecules are forced apart. The carbon separates from the hydrogen entirely, and that liberated carbon, compressed brutally enough, does the one thing carbon does under sufficient pressure. It crystallizes into diamond. Tiny crystals of pure diamond, forming roughly 10,000 kilometers beneath Neptune's visible surface. And because diamond is denser than the surrounding material around it, those crystals don't float. They sink, falling steadily downward, deeper and deeper, toward the planet's core. An endless, silent rain of gemstones, falling through a superheated, supercritical ocean of crushed fluid, a rain that has been falling continuously for billions of years. Some researchers estimate that the accumulated diamonds gathering at Neptune's core could reach sizes measured in the millions of carats. Crystals of pure carbon potentially the size of mountains, sunk forever into the darkness of a planet that essentially nobody visits, holding what might be the single most culturally valuable substance humanity has ever imagined, falling in an endless downpour over a world where no one will ever be able to collect it. And this has been happening since before your own species existed in any recognizable form, back when the most advanced life on Earth consisted of simple bacteria drifting in ancient oceans. Somewhere beneath those violent blue clouds, that rain has never once stopped falling. Even Neptune's famous, striking blue color turns out to hide a small deception of its own. For decades, the images most people associate with Neptune, a deep, almost electric sapphire blue, were themselves subtly exaggerated. In 2022, researchers who carefully reprocessed the original Voyager 2 data, correcting for how those early images had been enhanced and combined for scientific clarity rather than strict visual accuracy, found that Neptune's true color is actually considerably paler and closer to the muted, greenish blue of Uranus than the vivid, saturated blue that became so iconic in public imagination. The genuinely deep blue we've all grown used to seeing was, in part, an artifact of image processing choices made decades ago, not an outright fabrication, but an emphasis that outlived its original scientific context and quietly became the planet's popular identity instead. Even Neptune's most basic, most recognizable feature, the very color it was named for, turns out to have been slightly overstated the entire time we thought we knew it. Neptune has one more secret buried inside it, one that Voyager 2 stumbled onto almost by accident, and it might be just as strange as the diamond rain, if considerably less romantic. Every planet with a magnetic field that we'd studied before Neptune shared a basic, comforting pattern. The magnetic field lines up reasonably close to the planet's actual axis of rotation, and it originates from somewhere near the planet's center, the way Earth's own magnetic field roughly aligns with its geographic poles. Neptune broke that pattern completely. Neptune's magnetic field is tilted a staggering 47 degrees away from its axis of rotation, and it isn't even centered on the planet at all. It's offset, shifted dramatically off-center, more than halfway out toward the surface in one direction. Imagine a bar magnet, not sitting neatly at the center of a spinning ball the way you'd expect, but shoved lopsidedly off to one side, and tilted at a bizarre angle on top of that. As Neptune rotates, this strange, off-kilter magnetic field wobbles and tumbles through space in a way that looks almost chaotic from the outside, nothing like the clean, stable magnetic fields of Earth, Jupiter, or Saturn. The leading explanation is genuinely unsettling in its own quiet way. Rather than being generated by a solid metallic core the way Earth's magnetic field is, Neptune's field may be produced in a relatively thin shell of electrically conductive fluid, superheated water, ammonia, and methane, compressed into a strange, conductive slush somewhere in the planet's mid-depths, rather than deep within a stable, well-behaved core. If that's true, Neptune's entire magnetic field is being generated in a genuinely turbulent, asymmetrical layer, one that behaves almost nothing like the tidy magnetic dynamos found elsewhere in the solar system. Uranus, Neptune's closest planetary sibling, shares this same strange, off-center, wildly tilted magnetic field, suggesting that ice giants, as a category, might simply generate their magnetism in a fundamentally different, Messier way than rocky planets and gas giants do. Even Neptune's magnetism, the invisible field surrounding the entire planet, refuses to behave the way physics textbooks originally assumed it should. Neptune has 14 known moons. 13 of them are unremarkable in the grand scheme of things, small, irregular, orderly, all quietly orbiting in the same direction as the planet's own rotation, exactly the way moons are supposed to behave. And then there's Triton. Triton is Neptune's large moon, nearly the size of our own moon, and it does something no other large moon in the entire solar system does. It orbits backward. Every other major moon in our solar system, our own moon, the large moons of Jupiter, the large moons of Saturn, the moons of Uranus, orbits its planet in the same direction that planet itself rotates. That's the natural direction, the direction left behind by the way the solar system originally formed. Everything spinning and orbiting together in the same rotational sense, like water draining consistently in one direction. Triton spins the opposite way entirely, and there's really only one explanation that makes sense of that. Triton wasn't born alongside Neptune. It almost certainly began its existence as an object from the Kuiper Belt, one of those distant, frozen worlds, not unlike Pluto, that drift through the icy outskirts of the solar system. At some point, billions of years ago, Triton was traveling alone out there, until it wandered too close to Neptune. Neptune's gravity caught it, seized it, and forced it into orbit, but caught it badly, in reverse, locking it permanently into a backward path around the planet that captured it. And ever since that capture, billions of years ago, Neptune and Triton have been locked in a slow, silent, entirely one-sided war. Because Triton orbits backward, its relationship with Neptune's gravity is fundamentally unstable, in a way that no forward-orbiting moon ever experiences. Instead of gradually drifting away from its planet the way our own moon slowly recedes from Earth, Triton is doing the opposite. Neptune's gravity is steadily, patiently pulling Triton inward, millimeter by millimeter, year after year. It's an almost imperceptibly slow process, so slow it looks, on any human timescale, like nothing is happening at all. And yet it's utterly inevitable, and it already has an approximate expiration date attached to it. Somewhere between 100 million and 300 million years from now. Estimates vary considerably. Triton will finally drift close enough to Neptune to cross what's called the Roche limit, the exact distance at which a planet's gravitational tidal forces become strong enough to overpower a moon's own internal gravity holding it together. Once Triton crosses that boundary, Neptune's tides will begin tearing it apart, piece by piece, layer by layer. The entire moon will eventually be shredded into a brand new ring system encircling Neptune, not unlike the rings of Saturn, but built from the disassembled corpse of an entire captured world. Right now, tonight, we're living inside the only window in all of cosmic history when Triton still exists as a moon. When our distant descendants eventually point far more advanced telescopes at Neptune, they won't see Triton there at all. They'll see the ring it eventually became. Triton is being quietly, patiently dismantled in extreme slow motion, and it has absolutely no way of knowing that. Triton's doomed fate isn't even the strangest thing about it. During Voyager 2's brief flyby in 1989, its cameras captured something else entirely unexpected on Triton's frozen surface: active eruptions. Geysers, several kilometers tall, erupting directly from the icy crust, launching dark plumes of nitrogen gas and dust straight up into Triton's thin atmosphere, where high-altitude winds then smeared them out sideways for tens of kilometers, leaving long, dark streaks scattered across the moon's pale, icy surface. Triton, sitting in one of the coldest, most remote corners of the entire solar system, with a surface temperature hovering around -235 degrees Celsius, one of the coldest measured surfaces anywhere among the planets and their moons, is nevertheless geologically active. Nobody fully understands the exact mechanism driving these eruptions. The leading theory involves seasonal sunlight, however faint, slowly warming a shallow layer of frozen nitrogen ice just beneath the surface until it turns directly into gas and bursts violently outward, like an icy geyser triggered by nothing more than the barest whisper of solar heating. A moon this cold, this far from the sun, simply shouldn't have anything resembling active venting at all. And yet, briefly, for a few hours in 1989, we watched it happening anyway. Triton's surface itself looked like nothing scientists had ever encountered on another world. Vast stretches resembled the pitted, dimpled skin of a cantaloupe, an unusual, wrinkled terrain that earned the informal nickname Cantaloupe Terrain, its exact origin still not entirely settled, possibly the result of dense, heavy material slowly sinking and lighter material rising through the icy crust over millions of years, in a process similar to how blobs move inside a lava lamp, just unfolding at a glacial, geological pace. Elsewhere, the surface showed remarkably few impact craters at all, a telltale sign of a relatively young surface, geologically speaking, one that has been repeatedly resurfaced by internal activity, erasing older scars, rather than an ancient, static world that has simply accumulated impact damage since the beginning of the solar system without ever changing. Beyond Triton, Neptune's other moons carry their own smaller mysteries. Nereid, one of Neptune's more distant moons, follows one of the most eccentric, elongated orbits of any moon in the solar system, swinging from relatively close to Neptune out to a distance nearly 10 times farther away, on a single, lopsided loop that some astronomers suspect may itself be a leftover consequence of Triton's violent, gravity scrambling capture billions of years ago. Proteus, one of the largest of Neptune's smaller moons, is so oddly shaped, more like an irregular, lumpy potato than a proper sphere, that it sits right at the theoretical boundary of how large an object can get before its own gravity should be strong enough to pull it into a rounder shape. Proteus itself remained completely unknown to us until Voyager 2's cameras spotted it in 1989. It's dark enough and sits close enough to Neptune's own glare that no ground-based telescope had ever managed to pick it out before that single flyby. It's a small, quiet reminder of just how much even one brief encounter can add to our understanding of a world. An entire moon, large enough to nearly qualify as round under its own gravity, sat completely undetected until a spacecraft finally passed close enough to notice it. And Neptune has rings too, though nothing like the bright, sweeping bands surrounding Saturn. Neptune's rings are faint, dark, dusty, and strangely clumped, gathered into distinct arcs rather than smooth, continuous bands circling the entire planet, clumping that shouldn't be gravitationally stable on its own, and that scientists still can't fully explain, likely held loosely in place by the subtle gravitational influence of small, unseen shepherd moons weaving quietly among the debris. There's one detail that quietly reframes everything you now know about Neptune. We have never gone back. Voyager 2, the only human spacecraft ever to fly past Neptune, launched all the way back in 1977, years before the personal computer existed in any meaningful household sense, decades before the internet, decades before the modern smartphone. It was originally built and budgeted to last just 5 years, with a primary mission to study Jupiter and Saturn. It didn't stop there. It kept going, sailing past Jupiter, past Saturn, past Uranus, and finally, 12 years after launch, it swept past Neptune at a distance of roughly 5,000 kilometers above the planet's cloud tops. For a handful of brief hours, its cameras and instruments were turned toward the planet, gathering everything they possibly could. Then it kept moving, sailing on past Neptune's largest moon and outward into the darkness beyond, toward interstellar space. That flyby happened in 1989. Nobody has returned since. Not once. We have the Hubble Space Telescope, we eventually had the James Webb Space Telescope. We have some of the largest, most powerful ground-based observatories ever built, and all of them occasionally turn their attention toward Neptune. We watch new dark spots appear and disappear. We track subtle shifts in its cloud bands. But all of that observation happens from an enormous distance, 4.5 billion kilometers away, roughly equivalent to watching an entire soccer match unfold from the vantage point of a distant satellite. The genuinely detailed knowledge we have of Neptune, the fine texture of its atmosphere, the structure of its faint rings, the surface details of Triton, all of it comes from that single narrow window in 1989. One spacecraft, one pass. Decades ago, Voyager 2 is still out there right now. Tonight, more than 20 billion kilometers from Earth and counting, its signal growing fainter with every passing year as its power source slowly, steadily runs down. Bolted to its side is a golden record, a physical disc engraved with sounds and images from Earth. Greetings in dozens of human languages, whale song, music spanning cultures and centuries, a deliberate, almost hopeful message tucked onto a spacecraft that was never really built with any expectation of being found by anyone at all. It's still carrying that message outward, past Neptune, past the edge of the sun's influence, into the true emptiness between stars, a small, golden postscript to the only close visit Neptune has ever received. At some point, likely within the coming years, Voyager 2's power will finally run out for good, and its own transmissions back to Earth will go silent. And when that happens, there will be nothing left anywhere near Neptune at all. No spacecraft, no probe, nothing but distant telescopes squinting across billions of kilometers, and the memory of a single brief encounter, captured by a spacecraft that was launched back when we still genuinely believed we'd eventually go back. There have been proposals over the years, serious ones, for a dedicated mission back to Neptune, something built specifically to orbit the planet, to study its interior, to watch Triton up close before it's too late, to finally answer some of the questions that single 1989 flyby only managed to raise. Concepts have circulated among planetary scientists under names like Neptune Odyssey and Trident, some proposing a full orbiter designed to spend years circling the planet and repeatedly studying Triton's surface up close, others proposing a leaner, faster flyby mission specifically timed to catch Triton at a favorable point in its orbit. None of them have actually flown yet. The distance alone makes any such mission an enormous undertaking. Depending on the exact trajectory and available rocket technology, a spacecraft launched today would likely still need well over a decade just to arrive, followed by years more of careful study once it got there. Funding, competing scientific priorities, and the sheer difficulty of operating a spacecraft that far from the sun, where solar power becomes essentially useless and everything must run on far more limited nuclear power sources instead, have all repeatedly pushed a return mission further down the priority list. For now, Neptune remains almost exactly what it was after Voyager 2 passed by, a planet we glimpsed once, briefly, and have been quietly wondering about ever since. Let's go a little deeper into what Neptune is actually made of, because even its basic classification sets it apart from the planets most people picture when they imagine the outer solar system. Jupiter and Saturn are gas giants, planets built overwhelmingly from hydrogen and helium, the same simple elements that dominate the Sun itself. Neptune and Uranus belong to an entirely different category, ice giants. Beneath Neptune's outer envelope of hydrogen, helium, and methane gas lies a vast, churning layer of what planetary scientists call, somewhat misleadingly, ices, not solid ice cubes in any ordinary sense, but a scalding, densely compressed fluid made mostly of water, ammonia, and methane, all held under such extreme pressure and heat that it behaves more like an exotic, superheated slush than anything resembling ice as we understand it on Earth. Deeper still, pressures climb high enough that this fluid layer may transition into something even stranger, an exotic state where water molecules themselves get stripped apart, oxygen and hydrogen forced into arrangements that don't occur naturally anywhere on Earth's surface. Some models suggest this deep layer may behave almost like a superionic fluid, where oxygen atoms remain locked into a rigid, crystal-like lattice, while hydrogen ions flow freely through it, conducting electricity in a state that's neither solidly frozen nor fully liquid in any conventional sense. If that model is correct, it may help explain Neptune's strange, off-center, wildly tilted magnetic field we discussed earlier, since a churning, electrically conductive layer like that, sitting relatively close to the surface rather than deep within a solid metallic core, could easily generate exactly the kind of lopsided, chaotic magnetism Voyager 2 actually measured. At the very center, Neptune likely holds a small, dense core of rock and metal, roughly Earth-sized, buried under such crushing pressure from everything above it that we have almost no direct way to study it at all. Everything we think we know about Neptune's deep interior comes from mathematical models, built from gravity measurements and laboratory experiments, rather than from anything resembling direct observation. Neptune and Uranus are often grouped together as siblings, and in many ways, they genuinely are similar. Comparable size, comparable composition, both classified as ice giants, both a strange, muted shade of blue-green caused by methane absorbing red light out of reflected sunlight. But the differences between them are just as striking as their similarities. Uranus rotates on its side, tilted at a bizarre 98 degrees, likely the result of an ancient, catastrophic collision early in its history, meaning its poles alternately point almost directly at the Sun for decades at a stretch as it slowly orbits. Neptune's tilt, by comparison, is a far more moderate 28 degrees, reasonably similar to Earth's own axial tilt, giving it seasons that unfold in a comparatively familiar pattern, just stretched out over an entire Neptunian year of 165 Earth years instead of one. And where Uranus appears comparatively calm and understated in its atmosphere, its internal heat source apparently weaker or better hidden, Neptune runs hot from within, restless, storm-racked, driven by that mysterious internal engine that keeps its winds howling at supersonic speeds no matter how faint the distant sun's warmth actually is. Two planets, built from remarkably similar ingredients, and yet one behaves like a quiet, tilted oddity, while the other behaves like something that never quite settled down. Given Neptune's 28-degree axial tilt and its extraordinarily long orbital period, its seasons unfold on a genuinely staggering timescale. Each Neptunian season lasts, on average, more than 40 Earth years. A single Neptunian summer, and the corresponding winter on the opposite hemisphere, stretches out over roughly 4 decades before the next season even begins to take hold. Southern Hemisphere summer on Neptune began sometime around the year 2005 and is expected to continue for years still to come, meaning an entire human childhood, adolescence, and early adulthood could unfold on Earth within the span of a single Neptunian season change. Astronomers have actually detected subtle seasonal shifts in Neptune's cloud activity and brightness over the decades since Voyager 2's flyby, evidence that despite its ferocious internal weather, the planet still responds, slowly and faintly, to whatever thin trickle of sunlight actually reaches it across such an enormous span of orbital distance. It's a strange thing to consider. Somewhere on Neptune right now, An entire season is quietly unfolding, one that began before some of the people listening to this were even born, and that won't fully conclude until long after this particular night has been forgotten. That discovery story deserves a little more detail, because it wasn't quite the tidy, single moment of triumph it's often remembered as. The French astronomer Urbain Le Verrier and the English astronomer John Couch-Adams had, in fact, each worked out the calculations mostly independently, racing against each other without either one fully realizing just how close the other actually was. Adams completed much of his calculation first, but struggled to get British astronomers to take his predictions seriously enough to actually search the sky with any urgency. Le Verrier, working separately in France, sent his own calculated coordinates directly to an astronomer at the Berlin Observatory, who pointed his telescope at the specified location on the very first night he tried, and found Neptune sitting almost exactly where the mathematics said it should be, within about 1 degree of the predicted position. What followed was a genuinely tense, prolonged dispute over who truly deserved credit for the discovery, a rivalry between French and English astronomy that took years to properly settle. Eventually, both Le Verrier and Adams came to be recognized together as co-discoverers, a rare, hard-won example of two independent scientific efforts arriving at essentially the same extraordinary answer, using nothing but careful mathematics and an unshakable trust in Newton's laws of gravity, aimed at a patch of empty-looking sky that turned out to be hiding an entire planet. Neptune also holds one of the coldest confirmed temperatures ever measured anywhere in the solar system, though perhaps not quite where you'd expect it. While Neptune's average cloud top temperature sits at a brutal negative 214 degrees Celsius, cold enough on its own to freeze nearly every gas we're familiar with solid, it's actually Neptune's large moon Triton that holds one of the true cold records among all the worlds we've measured directly, its frozen nitrogen surface dropping to roughly negative 235 degrees Celsius, just a handful of degrees above absolute zero itself, the theoretical point at which all molecular motion would completely stop. At temperatures that extreme, ordinary materials behave in genuinely alien ways. Nitrogen, the same gas that makes up most of Earth's breathable atmosphere, exists on Triton's surface as solid ice, and in certain places as a thin, wispy atmosphere of nitrogen gas that occasionally, as we discussed earlier, erupts violently upward through Triton's crust in geyser-like plumes. It's a genuinely strange contrast to sit with. A planet driven by ferocious internal heat and screaming supersonic winds, quietly orbited by a moon so cold that its very atmosphere exists on the frozen edge of physical possibility. Neptune's atmosphere doesn't just host its wandering dark spots. It's also organized into distinct bands of jet streams, much like Jupiter's and Saturn's, alternating belts of eastward and westward winds circling the planet at different latitudes. But where Jupiter's bands tend to be relatively stable, tracked and mapped in detail for centuries, Neptune's jet streams appear considerably less predictable, shifting in strength and position more noticeably over the decades astronomers have been able to observe them. Small, bright clouds of frozen methane crystals occasionally form high in Neptune's atmosphere, drifting rapidly around the planet, giving scientists a way to actually measure those ferocious wind speeds directly, tracking individual features as they race across the disk of the planet from one observation to the next. It was exactly this kind of tracking, combined with instruments aboard Voyager 2, that first confirmed just how extraordinarily fast Neptune's winds actually blow. A world so distant, so faintly lit by the sun, and yet its atmosphere behaves like something perpetually enraged, banded into competing streams of supersonic air that never fully settle into calm. Let's slow down together for a moment. If any of these numbers, the wind speeds, the distances, the billions of years, have started to blur together, that's all right. There's no need to hold on to every figure precisely. Let the shape of the story settle instead, a distant blue planet, driven by forces from deep within itself, indifferent to how far the sun's warmth actually reaches it. We have just a little further to go tonight, back to that one brief visit in 1989, and then gently to a close. There's one more reason Neptune deserves more attention than it usually gets, beyond its own considerable strangeness. As astronomers have discovered thousands of planets orbiting other stars over the past few decades, one particular size category has turned out to be almost startlingly common throughout the galaxy. Worlds roughly between the size of Earth and Neptune, informally nicknamed sub-Neptunes. Our own solar system, strangely, doesn't contain a single planet that falls neatly into this size range. There's a genuine gap between rocky Earth and gas-rich Neptune that our own system simply skipped over. And yet, out among the thousands of confirmed exoplanets discovered so far, this in-between size appears to be one of the single most common types of planet in the entire galaxy, far more common, by current counts, than planets closely resembling Earth. Which means Neptune, the planet almost nobody thinks about, may actually be one of our best available templates for understanding an entire, enormously common category of worlds scattered throughout the Milky Way, planets we can't visit, can barely photograph directly, and mostly have to understand by comparison to the one ice giant close enough for us to have actually studied up close, if only for a handful of hours, decades ago. Every distant sub-Neptune astronomer's catalog today gets interpreted, at least partly, through hints borrowed from that single Voyager 2 flyby of our own quiet, overlooked, furious blue planet. There's an even stranger possibility hiding inside that diamond rain we discussed earlier, one that researchers are still actively trying to confirm. If diamond crystals keep sinking steadily toward Neptune's core, accumulating there over billions of years, some scientists have proposed that conditions near the very center of the planet might eventually produce something almost unbelievable, an actual solid layer, or even a slushy ocean, of diamond, sitting at the boundary where Neptune's crushed, superheated interior meets its small rocky core. Some early laboratory experiments even suggested the possibility of diamond icebergs, solid chunks of crystallized carbon floating within a surrounding sea of liquid carbon, in a bizarre inversion of how ice floats on water here on Earth. Later, more detailed experiments complicated that particular picture somewhat, suggesting the reality inside Neptune may be messier and harder to pin down than a simple floating iceberg model would suggest. But the underlying physics, carbon compressed brutally enough to crystallize, then sinking or possibly pooling near the planet's core, remains one of the most striking, almost unbelievable details in all of planetary science. Somewhere beneath those howling blue clouds may sit the largest, least accessible diamond deposit in the known universe, and we may never manage to confirm exactly what shape it actually takes. Neptune's faint, dark rings deserve a proper introduction of their own, since they're so different from the bright, dramatic rings most people picture when they think of Saturn. Discovered gradually, first hinted at by ground-based observations in the 1980s, and finally confirmed and mapped in detail by Voyager 2 in 1989, Neptune's ring system consists of several thin, dusty, dark bands, later named after some of the astronomers connected to Neptune's own discovery and early study, Gall, Leverrier, Lassell, and Adams among them. The strangest feature of these rings isn't their faintness, it's their clumpiness. Rather than spreading evenly around the entire planet the way Saturn's rings do, portions of Neptune's outermost ring, named Atoms after one of the planet's co-discoverers, are gathered into distinct, dense arcs, several of them even given their own individual names: liberty, equality, fraternity, and courage among them. Clumps of material bunched together in specific stretches of the ring, with comparatively empty gaps in between. By any straightforward application of orbital mechanics, that kind of clumping shouldn't be stable. Over time, gravity and collisions should smooth the material out into an even, continuous band. Researchers currently suspect small, otherwise undetected shepherd moons, tucked closely alongside the rings, may be gravitationally herding that material into place, holding the clumps together the way a sheepdog holds a flock, though the fine details remain only partially understood even now. Even Neptune's rings, faint and easy to overlook, are quietly refusing to behave the way simpler physics says they should. It's worth asking, gently, whether a planet this violent could possibly host anything resembling life, and the honest answer is almost certainly not, at least not anywhere near its surface, or rather, its lack of one. Neptune has no solid surface to speak of at all. Descend far enough into its atmosphere, and gas simply transitions gradually into denser and denser fluid, with no clear boundary you could ever stand on. Between the crushing pressures, the supersonic winds, and the deeply exotic chemistry occurring in its interior, Neptune itself offers essentially nothing resembling a habitable environment by any definition we currently understand. Triton, oddly enough, draws slightly more genuine scientific curiosity on this front, not because anyone expects to find life there today, but because its icy crust, its evidence of past or ongoing geological activity, and the intriguing possibility of a hidden, subsurface layer of liquid water beneath its ice, kept warm by tidal flexing from Neptune's gravity, place it in the same broad category of interest as icy moons like Europa or Enceladus, worlds where a hidden ocean might exist beneath a frozen shell. No such ocean has been confirmed on Triton, but it remains, quietly, one of the more tempting mysteries still waiting inside the Neptune system. One more question that single 1989 flyby simply didn't have time to answer. There's a strange, almost fitting postscript to Neptune's origin story, one still actively unfolding today. Neptune, remember, wasn't found by patiently scanning the sky. It was found because Uranus's orbit refused to behave the way Newton's equations said it should, and mathematicians worked backward from that misbehavior to predict exactly where an unseen planet had to be hiding. In recent years, a strikingly similar pattern has emerged again, this time involving a cluster of small, icy bodies out in the distant Kuiper belt, whose orbits appear to be subtly, suspiciously aligned in ways that random chance alone struggles to fully explain. Some astronomers suspect this alignment could be the gravitational fingerprint of another undiscovered planet, informally nicknamed Planet 9, orbiting even farther from the Sun than Neptune itself, in some of the darkest, most sparsely searched territory the solar system has left to offer. No such planet has been confirmed yet, and some researchers remain genuinely skeptical the evidence holds up at all under closer scrutiny. But the method being used to search for it is precisely the same one that revealed Neptune back in 1846, watching for a gravitational fingerprint too consistent to be coincidence, then calculating exactly where the culprit responsible would need to be hiding. It's a strange thought to sit with. The very technique that first uncovered Neptune, mathematics quietly outrunning observation, may be on the verge of doing exactly the same thing again, somewhere even farther out in the dark, beyond the reach of the one planet we've spent this entire evening exploring together. Neptune will keep turning tonight, whether or not anyone is watching. Diamonds will keep falling silently through its crushed interior, exactly as they have for billions of years. Triton will slip one more fraction of a millimeter closer to its eventual unraveling. Somewhere in one of its hemispheres, a storm the size of an entire planet may already be gathering itself out of nothing, forming without a single witness. And its winds, its impossible, ceaseless, screaming winds, will keep tearing across its atmosphere at speeds no hurricane on Earth has ever come close to matching. An endless storm, without spectators, on the most violent planet in the solar system, and none of it will pause, even slightly, for our attention. That might be the hardest part of all this to sit with. Not that Neptune exists, not even that it's violent, but that it exists entirely without us. Its fury doesn't need our eyes to be real. We've spent 4.5 billion years arriving late to this particular party, and every indication suggests we'll be gone long before that party ever winds down. We gave this planet the name of the calm, deep-sea god, thinking blue meant peace, thinking blue meant something quiet and mysterious in the comforting sense of those words. Blue, on Neptune, turned out to be the disguise. Here's the mirror I want to leave you with tonight. The next time you happen to glance up at the night sky, remember that somewhere out there, in a direction your own eyes will genuinely never be able to reach clearly enough to see, all of this is still happening. Winds beyond anything Earth has ever recorded. Diamonds falling through darkness toward a core no one will ever visit. A moon quietly, unknowingly counting down toward its own transformation into a ring. None of it performing for us. None of it waiting for permission or attention or applause. The universe doesn't pause its most extraordinary events simply because no one happens to be watching. It just keeps happening, patiently, indifferently, whether we're there to notice or not. Tonight, you gotta notice, if only for an hour. That's enough. If this story helped your mind unwind, you're always welcome to like this video, subscribe to Somniora Mind, or leave a comment letting me know what part of tonight's story stayed with you. It helps other curious, sleepy minds find their way here too, one quiet mind at a time. Rest now. You've earned it. Good night.